Welcome to our lecture on cryptography. If you want to be a good cybersecurity specialist, you must have a good understanding of the fundamental concepts involved in cryptography. Cryptography is the study and application of methods and techniques to protect information by using codes for secure communication. So the bottom line in cryptography is to ensure secure communication between two parties. Cryptography is broadly categorized into two main categories, symmetric and asymmetric. We are going to start with symmetric encryption concepts. Symmetric encryption is also called private key encryption, and it uses the same key for encryption as well as decryption, and that is why it is called symmetric, because the same key is used both at the source and at the destination. It also uses the same cipher. Now, cipher is a word which is an alternate for algorithms, is used for encryption and decryption. So the same algorithm is used at the source for encrypting data, and the same algorithm is used at the destination for decrypting the data. Now, key lengths determine the strength of encryption, and usually the longer the better. Some popular private key ciphers include AES, RC5, and Twofish. Let's have a look at how symmetric encryption actually works. So we have a source which wants to send data to a destination, and it wants to encrypt that data before sending it. So at the source, we have a plain text file, which means it is unencrypted text and anybody can read it. So basically we use a key, which is kind of a secret code, which helps us encode this plain text. In addition to the key, we need an algorithm, which is basically going to take the key and the plain text data, and it's going to do some steps, some operations, in order to provide us with the ciphertext, which is basically the encrypted text. So using the key and the algorithm with plain text as the input, we get a ciphertext as output, and this completes the encryption part. Now the basic aim of encryption was so that we could transmit data over the public internet without compromising its confidentiality. So that's exactly what we did. We converted plain text into ciphertext, and then the ciphertext, which is basically encrypted data, and even if somebody gets a copy of it while it is flowing over the internet, they would still not be able to easily break it because it's encrypted. Now at the destination has received the ciphertext, which is the encrypted text, and the process now needs to be reversed. So at the destination, it needs to use exactly the same key which was used to encrypt the data. Consider it exactly like a numbered lock. So you really need to line up exactly those same numbers if you want to unlock it. So using the exact same key and using the exact same algorithm, we can decrypt this data. So we convert the ciphertext back into plain text, and this is called the decryption. And this is how the source is able to encrypt plain text data into ciphertext, transmit it over the internet, and then the destination is able to get back the plain text from the ciphertext. Perhaps the single most important factor which can determine the strength of encryption is the key length. The longer the key, the better. So let's say you have a password with X number of characters. For every character, you can select either from A to Z, which are basically 26 different alphabets, or digits 0 to 9, which are 10. So 26 plus 10, 36 possibilities for each of these cells or each of these characters. But computers, they need digital numbers, they understand binary numbers. So we always talk about bits. So we talk about key lengths in terms of bits. Since we're talking about binary, so every cell or every bit can either be 0 or it can be 1. So if you have a key which spans n bits, then it means you have 2 raised to the power n different combinations possible. Let's have a look at a comparison table which shows us how increasing key lengths make breaking encryption difficult. So let's say if you are selecting a key length of 56 bits, which means that you have 2 raised to the power 56 different combinations, and using a good state-of-the-art computer, you can break it in 20 hours. But if you increase the key length to 128, the possible combinations now jump to 2 raised to the power 128, and it would take 5 into 10 raised to the power 17 years to break it using the same computer. And say if you increase the key length to 256 bits, then you have 2 raised to the power 256 different combinations, which would take 7 into 10 raised to the power 56 years. So nearly impossible to break. So the bottom line that we need to understand is that it is always advisable and in fact recommended to use long key lengths. A very popular and state-of-the-art symmetric encryption scheme is AES, Advanced Encryption Standard. It is so strong that it is even acceptable for military purposes. AES offers various key lengths starting from 128, 192 up to 256 bits. The key length determines the strength of the encryption. So obviously AES 256 would be considered stronger compared to AES 192, for instance. AES has several implementations and it's widely adopted in the industry, and it is used in a large number of applications. In contrast to symmetric encryption, we also have another type of encryption, which is asymmetric encryption, also known as public key cryptography. Now, the main difference between symmetric and asymmetric is that in symmetric encryption, both the sender and the receiver use the same secret key. But the problem with those type of encryptions is that, let's say you want to communicate with 100 different people, then obviously you'll need to have 100 different private keys, and it becomes difficult to scale it, right? So the solution to that is public key cryptography. So what happens in public key cryptography is that, let's say you have a plain text document. So what you're going to do is that you're going to use the public key of the destination. So the destination, let's say it's a server, it has shared its public key, which is known to everyone in the world. And you basically encrypt your document using this public key, right? So now the thing is that with asymmetric encryption, anything that has been encrypted with a public key can only be decrypted by a private key, which is secret, right? So it's like asymmetric. You're not using the same key for encryption and decryption. You're using two different keys. So if you want to send a message to a destination which you want to make sure that it's encrypted, you need to encrypt it using the public key of the destination and then send this message over the internet. So even if somebody eavesdrop, on this message right here, it's not a problem. So at the destination is going to use its private key. Now this one is secret and it is only known to this, the destination. And once it basically decrypts this, so basically we have completed the decryption part of the process. Now, a couple of points to keep in mind. The first being that you cannot decrypt a message or a file that has been encrypted using a public key, using the public key again. So it only works with public key encryption, decryption with private key, and vice versa, right? Now, another important point which I want to clarify, which confuses a lot of people, is that, so let's say what happens if we go the other way around. So for example, if the destination encrypts a document using his private key, then is not basically encrypting it for the sake of secrecy, because everybody in the world, they have the public key and they can simply decrypt it, right? In this case, what we call this is called digitally signing the document, which basically means that this guy is making sure that if I encrypt a document using my private key, then only my public key can be used to decrypt it. So it's just sort of an assurance that this was, signed by me. So this document is really coming from me. Now that's what we call digital signatures. So in a nutshell, just to reiterate, in public key cryptography or asymmetric cryptography, if you want to ensure confidentiality, then you'll be using the public key of the destination to encrypt the message, which the destination can then decrypt using his private key. And these two keys are different. You won't be able to decrypt a message which has been encrypted with a public key using the public key again, right? So that ensures confidentiality. But if the flow is the other way around, if this destination is encrypting a document using the private key, then it just means that he's making sure that, telling people that I have signed this document, because everybody can decrypt this document using the public key. This is public knowledge, right? So in this case, We're not talking about confidentiality or secrecy. Now, a couple of important points which I would like to reiterate. The first is that if you want to ensure confidentiality, so basically what you need to do is that you need to encrypt the data using the public key of the destination or the receiver. And at the receiving end, the receiver is going to use the secret private key for decrypting the data. And please keep in mind the private key is completely different from the public key. Now the point that we're trying to make is that the data that has been encrypted by public key cannot be decoded with the public key, and it must use the private key at the destination for decryption. Now on the other hand, if a sender is using his private key to encrypt something, then it's not really for secrecy, because everybody in the world has the public key and they can simply decrypt it. In that sense, it's just called digitally signing a document, which basically means that the sender is saying that, okay, here is this document. I have encrypted completely, full document or maybe a small part of it. And so basically general public can simply use the public key of that sender and then decrypt or, check whether this document actually came from this sender or not. The point being that only his public key can be used to decrypt this document, not somebody else's. So that's the key point to understand. The magic is basically in special mathematical operations, which allow the use of two different types of keys. So basically the difference between symmetric and asymmetric being that in symmetric we have exactly the same key at both the sender end and the receiver end. However, in asymmetric encryption, we're basically using two different keys. So one of the reasons why we needed asymmetric encryption was because private keys cannot always be safely exchanged on public networks like the internet. So asymmetric encryption is required to create that initial trust, the initial encrypted end-to-end communication channel, over which you can even exchange symmetric keys and then use them later on for encryption or decryption. But for the initial secure and encrypted channel, you definitely need asymmetric encryption. Another reason why you may want to consider asymmetric encryption is because symmetric keys are not really scalable. So imagine if you are a user and you want to communicate with n different entities. So you'll be requiring n different symmetric keys if you're using asymmetric encryption. Because you need a different key for A to 1 communication, for A to 2 you need a different key, and so on up to n. So if you're talking to n people, you need n different symmetric keys. So imagine if you want to communicate with thousands of different servers, you'll need thousands of different keys. So it is obviously not a scalable solution. Now contrast that with asymmetric encryption. So if you're using asymmetric keys, you just need two keys and that's it. So one is the private key, which would be used by A, and the second is the public key, which is published to all the users and it is public. Some popular asymmetric solutions include Diffie-Hellman, which is used for key exchange between two entities. We also have RSA, which is used for actual encryption or decryption, and we have ECC, which is again used for actual encryption and decryption, and there are several others available as well. A quick recap on the differences between symmetric and asymmetric encryption. So in symmetric encryption, we always use the same key for encryption as well as for decryption. But in asymmetric encryption, we use different keys, private and public. In symmetric encryption, encryption and decryption algorithms or ciphers are exactly the same. But in asymmetric encryption, we have different encryption and decryption algorithms because we are using different keys for encryption and for decryption. A major problem with symmetric encryption is that it is not always possible to exchange keys safely, because to start the encryption process, the two ends need to have the same key, and there is no way to exchange these keys without incurring some sort of a risk. In contrast, asymmetric encryption can be done on public networks. In fact, it is designed for communication over public networks. One advantage of symmetric encryption is that it's very fast, whereas asymmetric encryption is a bit slow. And one of the reasons is because it's using different encryption and decryption techniques. Now, since symmetric encryption is very fast, so what we normally do is that we create the initial secure channel using asymmetric encryption, but once that is in place, we exchange symmetric keys or session keys, and then we use symmetric encryption for quick and efficient encryption and decryption of data at the two ends. But for the initial establishment of the trust of the secure channel, we use asymmetric encryption. And then within that tunnel or within that channel, we can exchange symmetric keys as well. Another difference between the two encryption schemes is that for offering the same strength, symmetric key encryption requires smaller key lengths compared to asymmetric encryption. And this stems from the fact that asymmetric encryption is designed to allow for two different keys to encrypt and decrypt. So that's why we generally need longer keys in asymmetric encryption in order to provide the same level of safety as symmetric encryption. So that concludes our lecture. I'll see you in the next one.